Микрофон работает. Я вот заранее включил, чтобы в этот раз не было. Вот. Трансляция. Вот сейчас вот красненько включилась. Так, ну хорошо. Ну хорошо, давайте. Как? Значит, вы хотите больше четвертую. Давайте так сделаем. Значит, вы расскажете первую, я вторую, вот, а третью не знаю, потом вы четвертую, а потом третью, как получится. Такой план. Просто первая, вторая, это так, чтобы ускорить процесс следующей лекции. Вот. Но это связано как бы с предыдущей, но и хорошо, что вы посчитали. Значит, какой второй? Связано. Прям сильно. Да. Ну хорошо. Давайте тогда, Николай, вы первый расскажете, хорошо?
In the first part, I have to prove that firstly, I would like to notice that for any vector spaces with V1 and so on, VR, such thing is equal to this. I suppose that it is a well-known fact, and the map from here to here is such: if I have such tensor, then it acts on a such tensor by applying AI to VI. Hence, yes, and what is this? It is spent by such B. I can take any basis matrices here only, and it is by definition. And I need to check that SK preserves such B, but what it arbitrary we can consider arbitrary matrices from here. Yes. Произвольно. But in yes, but it is enough to consider only basis. And what is it? it is no, I would like to consider such thing. So I apply b to here and then apply tau, and it is by definition b is this. Yes, yes, it is b. Yes, and I
Tau is an element of permutation.
no, I apply b to such vector.
Yes. And then you
and then permute,
yes, okay.
and I get why he is tau in -1 degree, because if I permute such vector, then v1 goes to the tau 1's place. So on the first place it will be such vector. And of course it is equal to
So now we now moving that the right hand side will
yes, such thing. Yes, and what it is equal to if I delete tau -1 here, because the set of all yes, and here I can erase here and here, and I will get what I wanted is b applied to tau. Hence I have proved such inclusion. And in the other direction, oh, because if I have such a vector, then I would like to permute them, and then vi goes to the sigma i's place. But in the first place, to this place, and in the other direction, I would like to, of course it is almost obvious, I can write bi in such form, and I know that tau -1 b, tau is equal to b. No, it is the definition of this. Now I prove.
Who's B? Yeah, so you're.
It is another b.
So you're taking B from here.
From here, and
you would like to write it like that.
yes, I can write it like this, and I know this. But what it means?
You can write
It means that
and the goal is to write somehow like.
yes, it means that I can do such computation here and get so I permute indices, but it means that B lies in SK. It is another definition of such thing. It is such operators which in the second part, of course, I can write such thing. We have, this is an element from Lie group, so we act on each, not by Leibniz rule. And yes, and this means that such vector span some subrepresentation in SK Sn. And since it is irreducible, they span all SK Sn. The third part.
I don't know.
Okay. In the third part, it is most interesting. I have such a thing, and I would like to prove that it lies in G. Yes, and it is enough to prove it only for diagonalizable X, because it is some subspace, and diagonalizable are it is closed, of course, and diagonalizable are dense among all. So it is enough to consider. Of course, I can choose another basis.
G capital here is an image of UGLN, right?
Yes, 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 and of course I can choose any basis and consider only such matrices, not diagonalizable but diagonal. And
Explanation to the second part. It just don't understand actually. Why you proved
no, the first part it is enough to
The second part?
Yeah.
So we can take span of all these tensors.
U tensor U.
Yes. And know that if we apply G to this tensor, we obtain the tensor of the same form. So
Why is it
Oh.
why is it equal? Actually.
By definition, how do you
G
find
is
this?
element of this.
Isn't GX like GU tensor U?
No, it's algebra. The algebra acts like you were saying, but the group acts like this.
Okay. Oh, okay.
and here we enough to prove for diagonalizable, and then choose a basis such that I have such matrix, and it is enough to prove that I would like to prove by induction that by such symbol I would like to denote such thing. Simply symmetricalize this. And it is enough to prove that such things lies in G for diagonal X.
So like x1, xr, it's some diagonal lies in
No, diagonal.
diagonal endomorphisms, and 1, 1 is just identity.
Yes.
So you would like to prove that by induction on R?
Yes. That's, and if I take here all X, then I will get desirable. And for all ones it is clear. And now what is XR plus 1 acting on this? It can act on 1, so I get some A it is some natural number, and plus it is also some natural.
So now action is an action of algebra.
Yes, and it acts by Leibniz rule, so I can act on 1 and get it. Maybe I can on this one or on this one, so I get this some natural number, but it is positive, and all coefficients are positive. And so I get this, but all such since I already know how to get the lie in G.
Like you taken some element of diagonalizable element from endomorphism of C and act it on what, like space of endomorphisms.
No, it is.
So there XR plus
It is an.
is action. Or what?
It is an action. Yeah, no, it is such thing.
Yeah, S of this lies in something like what?
Yes, yes, yes,
And then you action on it by XR plus 1.
yes. In standard way.
But how do you act? Just left multiply.
Just left multiplication.
Yes. And
And where you use the diagonal?
not diagonalizable, but diagonal. Because the product of two diagonals is also diagonal, and I can't claim this for simple diagonalizable.
Yeah, but if like what if they just all lines? Why we need to prove it only for diagonalizable? What if x will be any matrices? Is it the same proof work? Yeah, yeah.
Yes.
Why this proof doesn't work?
Yes, maybe. Yeah, of course. Yes, yes.
Okay, so
It works for any matrices. Yes. So it is more simple even. So I don't need this, and I don't need part 2. We have proved it for any.
So okay, what again? So to grab the logic. So you would like to see that x tensor blah 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 tensor x is in G, and you prove by induction that any on R that any such thing, right, is in G.
Yes, and I act by xr plus 1 on such thing.
Yes, but yes, okay. Then you, this you know already that it's in G.
This
one
I want
is,
to get.
yes, this one we would like to get, but
And
this one is in G because
it is a representation. It is an image of UGLN. So it is.
yes. So this one is in the image.
Yes, it is in G. This. And all such things are in G. Hence, it is also in G. And so I proved it. I don't need the second part. And the fourth part I proved.
So what did you prove? So you proved that x is in
That
G.
this, yes, I proved that any such element lies in G.
Yes. Yeah, you do. That's cool. Well, I had something else in mind, so that's why I needed number 2.
Yeah, and so you didn't like use number 3 also to number 4. Yeah. Yeah, you proved number 3, but did you use like this proof that you say in number 3?
This number 1 proves that G is.
So let me maybe show what was how to use two, since we have it already. So. А? No, where? Мы доказали, что все вот S от x1 и так далее xr, они лежат, ну, они лежат в G. Вот, нам хочется доказать вот это равенство, вот такое мы доказали.
Это мы доказали.
Да, вот это доказали, хотим вот...
Нет.
Нет, вот это.
Это в первом.
Это первый. Сейчас. Нам нужно, что эндоморфизмы...
В одну сторону там очевидное включение.
Ну там вот.
Сейчас, извиняюсь, эндоморфизмы S... Да, в одну сторону, в принципе, более-менее очевидно. S каты, да, V бар это G. А G это как бы, ну, ро там от U G. Вот. Сейчас, в одну сторону очевидно, это в какую? Это вот в эту, правильно?
Да.
Вот. А с другой стороны, вот мы берем и сказали, что все вот эти S, x1 и так далее, xr, это, собственно, и есть элементы. То есть отсюда они лежат в G. Доказали какой индукс. Ну, собственно, я беру S. Ну, вот такой элемент, это все, как бы, грубо говоря, элементы. Ну, это базис, ну, как не базис, а образующий множество. Вот, оно и состоит из вот таких S.
Да, если честно, я тогда немного вообще запутался. А нам хоть что-то нужно, кроме вот этого маленького доказательства?
Нет.
То есть вот это оно все, да, окей.
Ну, это прикольно, это не то, что, да, хорошо. Вот.
Ну, первая часть там нужна была.
Первая часть тоже, видимо, не нужна.
Нет, нужно практически очевидно.
Нет, сейчас, мы же доказывали вот это вот равенство эндоморфизмов в S чертой СК, да, и G. В одну сторону это понятно, в другую сторону это вот этим доказывается.
Ну нам нужно это просто, чтобы понять, что вот это правильно, ну, мы, собственно, когда вот это включение доказывали, говорит, что все элементы отсюда это такие S, ну мы пользовались первым. Но это как бы действительно такая, проверить себя, как бы, действительно, так, как бы такая более-менее очевидная вещь. Нет, сейчас, а как можно воспользоваться вторым? Вот так вот я предлагаю. Значит, у меня есть, я хочу воспользоваться, значит, симметрическими полиномами. У меня есть symmetric, recall, symmetric polynomials in x1, xn. Мне нужен n-то элементарный. Вот, это x1, x2 до xn. И мне нужен, как их называют? Ну эти просто power, степенные, как бы степенные, я уже не помню, как называется. Вот эти x1 в степени g.
Да, это редагирование.
Плюс
Многочленный, наверное,
вот. Ну, соответственно, у меня есть какой-то многочлен от p-итых, который я p большой тут назвал, вот, который мне даст EK. EN. Сейчас, а сколько мне нужно?
Ну, в смысле, вы от одного байса в другой байс переходите, да?
Не, мне нужно прям не, мне нужно К вот здесь, извините. У меня К переменных.
Да, я там снизу.
Здесь К. Вот. Да, я перехожу от одного в другой, но даже это как бы это генераторы, да, всех симметрических многочленов.
Да.
Вот. Но мне элементарно мне только вот это ЕК. Вот. А теперь, значит, как у меня действует, если у меня есть вот такая штука, вот, x, то, как действует, значит, GLN, плюс единичка тензор x, тензор 1 и так далее, и так далее. Вот. Если я такое введу, и я теперь возьму этот p, вот, и применю дельта от x вместо p первого, дельта от x квадрат вместо p второго, дельта от x катый вместо p катый. Вот я утверждаю, что это на самом деле будет x, тензор x и так далее. Ну, просто потому что... там нужно какой-то гомоморфизм построить вот отсюда, как бы у меня здесь стоит, как бы, вот, сейчас, какой у меня там гомоморфизм, какой-нибудь между алгебрами должен быть.
Может, там какой-то коэффициент.
Типа x-иты там переходят в 1 тензор. А вот это стоит на этом месте. Да. Вот этот вроде гомоморфизм из c, x1, x так далее, xk, в эндоморфизмы. Он такой, в общем, не канонический, какой-то специальный, но тем не менее гомоморфизм. Вот. И что? И все. Это значит, что вот эти все друзья, они лежат в G. Потому что если я возьму что-то, какую-то матрицу в GLN, вот, и к ней применю дельта, вот, это именно так, как она действует на эндоморфизмах, соответственно, значит, вот я утверждаю, что дельта от x вообще любой матрицы NN из GL. Ну, просто потому что это так, как она действует. Это так, как GL действует. Вот. Но значит, и P от этого тоже лежит в нем. Значит, вот эта штука лежит.
Ну окей, а как из третьего?
А как из третьего, значит, ну, теперь мне нужно вторым воспользоваться.
Второй, четвертый, очевидно.
Ну, с второго, с третьего, ну как, мне нужно что-то сказать, наверное. Сейчас, момент. Так, что можно?
Но эти иксы, вот эти штуки в образе G лежат, и они все порождают.
Ну да. Да.
То есть, ну нет, ну так мы доказываем то, что как бы СК мономорфизмов содержится в G, да?
Да, обратное включение более-менее очевидно. Ну как, ну просто вот эта формула, которую написал, значит, само это действие, вот, я возьму там какие-то вектора, V1 и так далее, V2.
То, что оно,
То, что я проверю там для одной перестановки, у меня формула инвариантная. Вот, это мы уже делали, там даже можно несколько раз. Вот. Ну хорошо. Так. Всеволод, а вы не хотите никакую? Или просто послушать хотите? Так, ну нет, давайте сейчас вторую. Я думаю, так, ну давайте вы сначала четвертую расскажете, а потом значит, я. Ну, не важно.
На английском.
Да, давайте.
Okay. Where I can write? I think here. Or.
Doesn't really matter.
Yeah, okay. Well, we know that Q is one-dimensional, so it's spanned by some vector. Also we know that this vector is has weight something like lambda 1. We lies in V lambda. Well, Q lambda. Where lambda is something like lambda 1, lambda 2, lambda 3, and the sum is 3. Okay, then SL3 has
I think you can actually say what a lambda.
Yeah, I will say in the few seconds. Okay, SL3 has singular vector. Well, just like that. E13. Well, it's just the one in the 1-3 box. Okay, then Q tensor product with SL3 is spanned by vector V tensor E13. Okay, then if we say that this is L lambda, 1 minute, I will say it a little bit later. So yeah, we know how what weight has E13. It has weight mu, and mu looks like 1, 0, minus 1. Yeah, and if we say that Q tensor, so Q, yeah, this vector v, singular vector v tensor e1 free is lies in it has weight something like mu with apostrophe mu prime, and mu prime is something like lambda 1 plus 1, lambda 2, lambda 3 minus 1. Yeah, and so if we say that Q tensor SL3 is equal to some L lambda, and lambda should be should consist of only positives, integer numbers, that means that lambda 3 should be less or equal, more or equal than 1. Than 1. So it should be more or equal than 0, and that means that since lambda 1 less or equal than lambda 2 less or equal than lambda 3, that means that mu prime is just 2, 1, 0. Because it just cannot be anywhere else. And that means that Q is weight of 1, 1, 1. Because lambda 3 should be less or more or equal than 1, and lambda 1 should be more or equal than lambda 2, more or equal than lambda 3. It could be 3, 0, 0, 2, 1, 0, 1, 1, 0, 1, 1, 1.
Why the last one is 0?
Look, it's not 0. I say that mu prime, lambda 3 minus 1, should be 0. So mu prime should be 2, 1, 0. Well, I suppose if we like Q, it could be from this from what problem says, Q could be equal to something like L300, yeah.
Because E11 minus E22 acts by 3. But I said that every trace mismatches.
E11 minus E22, it acts like 3 then, yeah?
Yes.
Okay, yeah, you're right.
Lambda 1 plus lambda 2 plus lambda 3 is 1.
Is 3.
And lambda 1 minus
Lambda 2, 0.
0, lambda 2 minus lambda 3 is 0.
Okay. Okay, yeah, then because of it, yeah, of course.
Actually, I kind of made it to be 1.
Yeah, I understand. You just didn't say it, but made it. Yeah. Okay, yeah, then, okay, you're right. Then it should be something like this, but then everything, mu prime is still 2, 1, 0. Okay, then I want to say that, so we, so yeah, then V is equal to L lambda, if we say that this is equal to V. Yeah, so V is equal to L lambda since it has a singular vector of weight 2, 1, 0. So it's what L lambda is look like. So do we need to prove anything else to say that V is equal to L lambda? No, I think it's okay. And it's equal to L210. Yeah, now.
All of the same dimension if you just shift it by this vector 1, 1, 1. They're all in the same dimension. If you look, for example, to Weyl's dimension form, they are just all.
Yeah, dimension will be equal. Yeah.
Representations is just shift to this Q. Yeah, you can actually make Q to be like not like this 3. I wish.
didn't write, I think it.
Yeah, so this tree can be any number. So you
Yeah, so you can 2, 2, 2.
This is always tensoring with some one-dimensional representation.
Uh-huh.
So all these L lambdas, they're actually of the same dimension. So
Okay.
nothing else to change.
Okay. Yeah, and also, so we know also that singular vector is it should look like something like VT0, where T0 is 1, 1, 2.
Yes.
So yeah, and now H is spanned by something like E11 minus E22, E22 minus E33. That means that H tensor Q is spanned by something like, well, since Q is one-dimensional, it's just E11 minus E22 tensor V and another one. E22 minus E33 tensor V. Okay, now we need to understand what's how it's named, this diagram. Young diagram, yeah. What Young diagram?
Young diagram, we know already it's always of this shape, right? Now we need to understand what that.
Yeah, of course, it's Young tableau. So, yeah, and since we know that E11 minus E22 is equal to, it's equal to E21 of E32 of E13. Well, this, it's action.
Yeah,
So it's yeah, so you take commutator of it. Yeah, and it's just easy to see that this is minus E12, and then it will be what we want. So then that means that Young tableau for this vector is just E21 acted on E32 acted on T0. So that means that we need just to understand what is it, and since T0 is just E1 tensor E2, well, V T0 equal to this, we need to understand what will be E21 E32 action on VT0, and it will be E2 tensor E1 tensor E3.
Do you really want to write tensors, or maybe Young?
Oh, okay, I will just write Young tableau.
Yeah, Young tableau.
It will be prettier. Okay, it will be something like 2, 1, 3, and 1 minute.
First you add by
Yeah.
E32, so you replace
1, 2, 3.
that's already an answer, right?
No, it's not actually an answer because it's not semi-simple.
Yeah, but what do you do?
Yeah, and then
So
we.
this acts by replacing 2 with 3, and
Yeah.
that's it, right? And this acts by replacing each one with 2.
Yeah.
Okay.
No, that's what is it. Yeah, but this is not semi-simple. Semi-standard. It's yeah, semi-standard. So we need to say that 1, 2, 3 minus 2, 1, 3 minus 1, 3, 2 lies in R lambda, and that means that we can say that this equal to 1, 2, 3 minus 1, 3, 2. So it's 2 of 1, 2, 3 minus 1, 3, 2. Okay, and then we need to understand that another vector E22 minus E33 tensor V is just another one. It's just minus E32 E21 VT0. So yeah, and this will be okay. This will be minus this minus of 3, 1, 2, 2, 1, 3, 1, 3, 2, 1, 2, 3. So this lies in R lambda. Since it's just in one column we change the number, then that means that this will be just in our, when we quotient it will be just minus 1, 2, 3 minus 1, 3, 2. So this, and this is some basis vector of this, so it just looks like this. So, okay.
So the first one is just some exercise in computing determinants, actually. So, right, we need to check this. x1, x2, and x3 should I put equal to 1 equals sum over mu as mu x1, x2. So we need to check this. And mu here, so sum, so mu such that lambda, so mu is in between, parts of mu is in between parts of lambda. 2, 2, and lambda 3. Okay, let's try to do this. So first recall that what we have for S lambda. Let me actually use my notes. This. Yes. So this is, just as a reminder, it's determinant. Yeah, maybe I should have written this in the formulation of the problem because people didn't remember this. So lambda I, lambda j, xj lambda I plus n minus I over this similar determinant where you have no lambda here, n plus I. So, minus I, yes. Okay, so I just take the upper determinant is 3 by 3. So what do I do? It is like that. Numerator. Okay, I have x, x1, x2, right? So for some reason it's easier for me x1, x2, x3 in here, right? Lambda has 3 parts. To write as x, y, z, just to reduce number of indices. Let me have it like that. And then I have x, x, y, z, x, y, z, x, y, z. I'm going to write exponentials here. So I have lambda 1, lambda 2, lambda 3, and plus 2 here, plus 1 here, and plus 0 here. So, and everywhere similarly. Lambda 1 plus 2, lambda 1 plus 1, lambda 2 plus 1, lambda 3, and here lambda 1 plus 2, lambda 1, 2 plus 1, lambda 3. So this is what stays in the numerator, right? Okay. Then I do what? I put z equals to 1, so I actually can erase. I actually can erase this. So I make this 1. So 1, 1, 1. And I subtract the last column from the rest of the columns. So I subtract these 3 ones from this one and from this one. Then I get, first of all, I get x some power, or y to some power, minus 1. It's divisible by x minus 1 or y minus 1. So I can factor it out from each column respectively. So I have x minus 1 times y minus 1. And what's left? You will get x to the lambda 1 plus 2 plus x to lambda 1 plus 2 minus 1 plus and so on. So the first exponential is like that. Maybe plus 1 here. Plus 1 here, and then lambda 1 and so on. Right? And then respectively, I have here lambda 2, right, plus x to the lambda 2 minus 1 plus and so on. And here I have x yes, so x lambda 3 minus 1 plus and so on, plus 1. And with y respectively, right? And here I still have ones. Very good. So let me use maybe this board. Okay. Since we keep this order, let me not break it. Then what? Then I subtract the last column. I subtract this from this one and this from this one. Okay. So then what do I get? So second from first, and then third from second. Then I get x minus 1, y minus 1, and here I have x to lambda 1 plus 1, plus and so on, all the way to x lambda 2 plus 1, right? And everything else I subtracted. And here I have x lambda 2 plus 1. I'm sorry, lambda 2.
So you like subtract from the first the second one, and from the second one the third
one, yes. Plus and so on. So these are all mu's that I would like to create.
Yes.
this is all mu1 plus n minus 1s. Okay, this is all mu2s plus n minus 2. So these are all such things. And x to the power lambda 3 and x to the power lambda 3 minus 1 and plus 1. Similar to for y. And here I have 0, 0, 1, by the way. So how do I compute this determinants? It's actually this one, right?
So why it's like there's really like some.
So I claim now that this is actually sum over mu's, the same sum that I would like to see there, of determinant of xi. So now it's 2 by 2 determinant to the power mu I plus n minus I. So you can check. So mu1 runs from so this n minus I thing will give me plus 0 here or plus 1 here. Okay, this is this shift, and then I have mu1 runs from lambda 1 to lambda 2, between lambda 1 and lambda 2, and mu2 between lambda 2 and lambda 3. Yes. And what about denominator though? So in denominator just similar computation, except all lambdas are zeros, right? So I have x square y square 1 x y 1 and then 1 1 1, right? What I would like to see is that it is x minus 1 times y minus 1 times x y 1 1. Well, this is easy. Then I divide one by another. I'm sorry. So here, of course, I also have this factor x minus 1, y minus 1, which is still there. So I divide. So this is exactly determinant x j n minus I, where ij run from 1 to 2. So this one. So if I divide one by another, this factor will cancel, and I will get exactly what I need.
X minus y minus 1. It will be x minus 1.
Yes. Mm-hmm. Seems like we did this exercise. But the thing is, it works. It's just easier to show it like that. But it works for any n, not only 3. It's just the same exact procedure you take, and you can write the same formula, and this always will be mu in between lambdas. And we will need this for the lecture. But for now, let us see how this is related to what's called branching rules for GLN. So it's almost the same, right? Because like you have on the left, you have character of representation. So what I would like, so I have inclusion, right, GLN minus 1, I mean 2 in this case, includes into GL3. Uh-huh. Yes, yes. Which exactly, I guess, well, it depends. So so we have E1, E2, E3, right? So I guess we look and this one negative 1 is H, right? And F1 here. So I guess we look at this SL2 triple, the first one, right? So this, and then they have something here, something here, something here. So this is my GL3. So my inclusion is this, right? GL2 is upper left corner. And so what Ciel says that if I take basically diagram for SL3, which is almost SL3 is almost the same as, and look at and forget about its. So I kind of project everything to this line, right?
Actually, I wrote it like that. Isn't it this one will be SL2
Maybe
SL2 sub-representation? This one, and this one.
Yes, but they are all. You can look. It depends.
Yeah,
you can choose.
One, choose this. I can
Yes.
always choose like
Yes.
this. Yeah. Okay.
Yeah.
That's true.
Symmetric. Kind of. Yes. Yes, but what it's what regarding this? So my character high lambda is dimension of the corresponding v lambda, right? X1 to the lambda 1, x2 to the lambda 2, x3 to the lambda 3. But now, so how do I look at this and obtain, so this is sum over, no, I'm sorry, v lambda here, and I have mu like that, right? Mu2, mu3. Okay, so what now I would like to see that if I now consider my v lambda as a representation of GL2 using this inclusion, I just need to put x3 to be 1. Why is that so? So let me see. So I take a vector, some vector from here, right? And it's inside GL2. I still have E11 and E22, right? And corresponding weights of this vector will be this mu1 and mu2. But what is the mu3? We don't care, because we don't have, we just don't care. We forget about this part. How not to care about some part of a polynomial? Just put this entry to be 1. And it just counts all, like it just sums up all vectors with if they had different this part, now they just sum up to give like more dimension into here. So high lambda GL2 is some dimension v lambda of mu x1, x2. It is high lambda of x1, x2, 1.
Yeah, so like if our character is, we did it like, we make it to the sum of some other characters, yeah?
Yes.
Like by the first part.
Uh-huh.
So why we know that there is no other sum of some characters to...
Yeah, because we proved on the lecture that I mean this the
for tensor product or something.
no, we proved that high lambdas are form a basis of CPW. So the composition, like whatever whatever thing it can be tensor thing, can be whatever. If it's some representation that has of a finite dimensional representation, it is in CPW, right?
So this basis is...
Yeah, no others. Yeah. Okay. So yes. Okay, so let's do 15.3 or yes, at least some part of it. Or maybe, Nikolai, you want to. Okay.
The first part is very easy because we know that E epsilon G epsilon E KL is equal to and I need to check it for this. But it is also true because if I apply the on the G to this, I can derive the K, and I will get such thing, or I can get D in square, but multiplying by the T, the K, and they will co-remove. So it is clear that GLN it is.
The square part is subtracted.
Yes, it is common for both. And we prove that Pn that P n is a G module. I can consider homogeneous polynomials of degree k, and of course it is also GLN model because such thing doesn't change the degree. And I would like to prove that it is irreducible. And for this purpose, I need to find all singular vectors. And how does that E does it G acts on something zk in degree m? It replaces z or it acts only on this, and it replaces one of the j on zi, and we consider only I lower j. So the numbers become less. And it is clear that the singular vector is only this. It is only one.
How you get from Z1k, Znk? I understand. How you get it?
So if I have something else,
Why Z2k not a singular?
because I can act by Z1, the Z2, and replace Z2 by Z1.
Yes, but can you act by Z2, D, DZ1?
No, singular vector is that if I act by each of these, I will get 0.
And why Pn is isomorphic to SCn? So you prove the irreducible decomposition, yeah?
Yes.
And in the first part there's another question about
Oh.
isomorphic to symmetry algebra of Cn.
Yes, it is clear.
So you have
No, it is what it is by definition. Pn is by definition as SCN.
Yeah, but why by SGLM models? So that's that they are as vector spaces are equal. I understand it, but why SGLM models?
Because I write this that it such thing it changes that I the j on that I.
I think you
and
just can take EI
that I.
to ZI.
Yes.
That's what isomorphism.
Yeah.
And in the second part, it is quite short. I have a yarn tableau, something like this, where E11, E21, and others. And then we construct dt, which is a product on J. And this thing is a determinant of such matrix. And what is JLN action of EG on T? It replaces G by E. So what, but only in one cell, in one particular cell, then sum all results for all such cells. So if we compute D on then in every such scene, only in one column that mg would replaced by zmi. But only
Whole column, yeah?
yes, but only in one column, because every cell here gives us one column. For example, this corresponds to this column, and we replace and do this on a Leibniz rule, because we for one cell, for another, and etc. And for determinant. But what is the action of EG on DT? Yes, on Pn it replaces the G by ZE. But if we consider Pn in 10th degree K, it replaces ZMG in by ZMI in the m's component, and it corresponds to derivating dt by zj, not by zj, but replacing this on this by Leibniz rule. So we have proved that it is the same thing.
So isn't you like proving that the fact about isomorphism, yeah? Not about homomorphism of GLN models?
Becomes interesting.
No, we have one module on which there are two GLN actions,
Yes.
and I prove that they're the same.
Yeah,
Well,
that's
yeah.
about isomorphism of PKN and PN tensor K, yeah? Then there's another question. Prove that the linear map is homomorphism.
No,
Yes, so that's exactly that was explained.
Yeah.
Just so you have, yeah. So how EIJ acts on DT. So that's what you need to
Yeah,
check.
that's
If it coincides with how EIJ acts on tableau, then we're done. Then it's
yeah.
homomorphism. So that's exactly what was checked.
Okay.
So let's have a break. Давайте сколько нам надо? Давайте 5 минут. Так. Нет, я не на многих защитах был, но непосредственно в той значит, скорее мой опыт такой, что там как бы человек очень сильно теряется, как бы, и люди не очень сильно стараются искать ошибки, потому что тогда он совершенно... Тогда просто защита прекратится. Вот. Так что, ну нет, не знаю. Ну, скорее наоборот поддерживает. Комиссия наоборот скорее поддерживает защищающегося. Вот.
Оценку комиссия выставляет?
Оценку, да. Сейчас. Я тоже был на вышкинской защите, я только на одной был, вот, как кандидатская. Сейчас. Да, это аспирантура, скорее всего.
Аспирантуре?
Да. Ну вот Ленин, значит, студентка Инна Машанова защищалась. Вот. Это единственная вышкинская защита, которая остальные там в Штатах.
Ну, мне просто интересно.
Существуют ли какие-то защиты, когда там выносят вас человек?
Да.
Я думаю, что существует, наверное, где-нибудь в MIT. Но я лично свидетелем не был.
Люди, которые в комиссии сидят, они видят отзыв рецензента? Ну, то есть, условно, я могу, то есть, может быть,
Они
рецензент
сами
пишет, что
пишут.
все плохо там.
Сейчас, в комиссии сидят люди, которые сами же писали отзыв.
Да?
Да. То есть, например, вышка стоял так, что нам как бы есть комиссия, нам высылается диссертация, вот мы их изучаем и пишем свое мнение. Потом как бы те же самые люди присутствуют на защите.
Это не диссертация.
Да.
На диплом, наверное, попроще.
А вот диплом не знаю. Это вы из личного интереса, да, спрашиваете?
Да. Просто через 2 недели защиты ничего не знали. Сколько по времени будет, что рассказывать.
Ну, такие стандартные вопросы, кто там умеет какой-нибудь Клименко отвечать? Или Граденцев?
Нет,
Вы не в магистратуре, вы в бакалавриате еще. Да.
Нет, я думаю, напишем какого-нибудь.
Ага. Я свой бакалавриатский диплом защищал на физфаке с ПБГУ. Вот, и там просто как бы никто ничего особо не понимал, вся сложность была в том, как бы это... Ну, в смысле, у меня математический был, значит, диплом. Вот. Рассказывал я физикам.
А как так получилось?
Ну, как бы там есть теоретические кафедры. Вот. Среди этих теоретических кафедр у меня была самая теоретическая. Вот и на этой теоретической кафедре научник у меня был вообще практически математиком. Вот. Ну, так и получилось. Нет, там есть кафедра матфизики на Сигме. Вот. Ну там люди занимаются там не алгеброй, а скорее какими-то аналитическими вещами, какие-то там вариации там каких-то задач там Штурм или Увиля, какое-то дифференциальное уравнение. Сложно. Но это не точно. Ну ладно. Ждем Марка, видимо, еще. Уже типа, если меньше 3 человек, то официально нельзя, наверное, проводить ничего. Ну, как бы, вроде бы такое, что типа курс должен состояться, если есть 3 слушателя. Может быть, это неправда.
Ну, на функциональном анализе, во второй части, слушателей обычно было 2
А.
или 3.
видимо, ну, может быть, формальная правда, но по сути неправда.
Плюс еще же есть люди, которые в теории, можно быть сколько угодно людей, которые отрицают систему.
В теории, да.
У всех этих людей там откуда-то по 100 просмотров набирается.
Может быть, там какой-то один сумасшедший человек просто 100 раз посмотрел. А он считает, интересно, он с одного IP, если 2 просмотра, он это как за 2 посчитает? Или нет?
Раньше так было. Сейчас, по-моему, полвниз там. 97, кажется, 67. 105.
Чё себе. Может быть, это эти... Сейчас.
Не, ну, я думаю,
My plan for the rest of the course. So today I would like to hopefully finish all these combinatorics. Yeah, so I think it should rather go in the first semester, maybe. We'll see. Like for the future, since it's like for GLN. Yeah, so today finish this. So discuss also Schur-Weil duality. So where is Igor? He wanted, I think, something like this. Yeah, he knows it. So yeah, and then maybe so we'll talk about infinite dimensional algebras for like 3 other lectures. So the next year, I think there will be some lectures on affine Cos-Modular algebras. Yes. So will be more of this. So junior.
Yeah.
Mm-hmm. Okay.
Yeah. Cos-Modular algebras, it's some connected Lie algebras, yeah.
So they are Lie algebras first of all, and if you try to, invent some infinite dimensional Lie algebras that behave like structurally like semi-simple Lie algebras, you end up with Cos-Modular algebras. But they have almost everything that have semi-simple Lie algebras and representation theory, but something more, like interesting stuff. Yeah, so we'll try to see what is this more, if time permits. Yes. But so for today, let us finish this business to not let it hang on. So yeah, so what was the story? The story was that we had this representation V bar, which is k copies of Cn. So this is a representation of GLN and Sk simultaneously, right? And we considered some sub-representation that we called R lambda, quotient by it. And so the goal was to see that this is actually L lambda. And we found a single vector inside and proved that it is really a single vector in the sense that it's not zero. But what was left is to compare dimension of two things. So to compare dimension of these two things, we found some spanning set in here. So this was VT bar. So this is the same as span VT bar, where T is semi-standard Young tableau of shape lambda. So now we would like to compare dimension of this with actually the size of this spanning set, right? Because so this is the question mark. This is what we would like to see, so we have that number of semi-standard Young tableau of shape lambda is greater or equal than dimension of this quotient, right? Since this is a spanning set. And this is greater or equal than dimension of L lambda, because L lambda is sub-module in here. That it is submodel, yes, we proved it when we showed that this has single vector of weight lambda. Therefore, it generates L lambda. Maybe something else. We would like to see that there's no this something else. And so we want to see actually that SSYT lambda size of this equals dimension of L lambda. Then we prove what? Then we prove that this question mark we confirm. And we prove also that this set, spanning set, is actually basis. And have another formula for, like, a description for dimension of L lambda, and ways to construct a basis. So how to do this? Well, this we do by proving the following proposition. S lambda of x is sum x to the weight of t as t runs over a semi-standard Young tableau of shape lambda. So here x to the weight t is x to mu x1 to the mu1, x2 of t, x2 is to the power mu2 of t, and so on, where mu I of t is a number of i's in t.
Sorry, what is weight of t?
So this is this as a whole notation is this. So weight of t is a vector or a tuple. The first entry is a number of ones in the tableau. Second entry is number of twos in tableau, and so on. Yes. Right. So we would like to see this. Sometimes in more combinatorial literature, this is definition of Schur polynomial, and then they can, by combinatorial means, they can prove that the other formula, which is the Weyl character formula, right? It's a ratio of determinants. But for us, we would like to prove that. And for this, we will need first lemma that will be easier to believe in after today's seminar. Lemma is like that S lambda of x1, xn is sum over mu S mu x1 xn minus 1 xn xn to the power lambda minus mu, where here the sum over mu such that we have this interlacing condition. Lambda 1 is greater or equal than mu 1, greater or equal than lambda 2, greater or equal than mu 2, and so on. And the last one is mu n minus 1, lambda n.
Yeah, and norm of lambda, it's the sum of lambda.
Yes, it's a number of boxes in its corresponding Kian diagram. Yes. How to do that? We just proof. We just first I claim that S lambda of x1, x2, x xn, xn, if I put this equals to 1, so just the last one, xn equals to 1. Right, so maybe let me write it like this, xn minus 1, and then 1. This equals to the same sum as mu x1 xn minus 1. So this is proved similarly to this n equals 3 example that we have. Okay, similar to seminar. But then from here we can go here easily by saying that S lambda is homogeneous polynomial of degree number of boxes in lambda.
Yeah, but is
It is clear from this, from just the definition. Over determinant xj n minus I. So each term on the top, you just sum over all I this, subtract sum over all I this. This will be a sum over all lambda i's. And and each term is like that. We know that they're divisible, like one divides another, so it's actually a polynomial in this case. But yes, okay. So, and degree of S lambda is length of lambda, I think sometimes it's called. No, length of lambda is usually a number of rows. So this is some, I don't know how it's, module of lambda, whatever.
I suppose it's usually said that it's a weight, like number of boxes is weight of tableau.
Maybe, yeah. Okay. We'll have too many weights then. Weight of weight.
Yeah.
Okay. But then since like that, from here this follows immediately. Very well. So therefore we proved lemma, right? From lemma, we would like to prove proposition. So proof of proposition. So obviously I would like to take lemma and apply it n-1 times. So apply lemma n-1 times. Then what we will get? Let me just write a formula. S lambda x1. It's not so bad, as bad as we think. So this is sum. What we get is actually a very well-known combinatorial object. It's called Gelfand-Zeitlin pattern. So sum over all Gelfand-Zeitlin patterns of lambda. So this is a bunch of partitions, n-1 of them actually. I will say what it is. So this is Gelfand-Zeitlin patterns of shape lambda. But all these lambda 1, lambda 2, these are all partitions of something. Not of k. Lambda is a partition of k, but all these are have Young diagrams which fits inside each other. Okay. And so x1 then I take to the power lambda n-1 minus lambda n-2, x2 to the lambda n-2 minus lambda n-3. Yes. Like this, and so on. So how to obtain Gelfand-Zeitlin pattern? I write first lambda maybe lambda 3 even here.
And x power of n, what will be?
Yeah, so it's not a power, it's a notation. So now it is sorry. So it's easier than you think. So it's actually like it's of the same sort as lambda, right? Lambda is a bunch of integers. So lambda 1 is also a bunch of integers. But what are restrictions for this bunch of integers lambda 1 that I take? I put it in such a triangle, and lambda 1 goes. So you just need to understand that I am applying lemma 1 many times.
Yes.
So the beginning of triangle is exactly like this. So I take lambda 1, 1, lambda 1, lambda 1, 2, lambda 1, 3, and so on. And so this one is greater or equal than this, or less. So this one is less or equal than this, and then I have this equality. So I have this and this,
So yeah.
and so on. So they are in between of the row on the top.
Upper index is n.
Upper index is 1. So this is 0, this is 1.
And then we will.
And the last one is lambda n minus 1. Yes, and again we have this.
And then we will have.
Lambda 2 is here.
Yeah, in this whole sum, what will be power of xn? Like xn to the power of what?
Yes, xn to the power of lambda. So exactly lambda minus lambda 1. This is exactly the power that we have here. So mu plays the role of lambda 1. It's the first step. And then we continue. And so we have a triangle like this. So such a data of numbers that actually in such correspond like inequalities is called Gelfand-Seytlin pattern. And it appears not only here, but in other.
So it should be in answer, so minus, like here, lambda n minus 1 minus lambda n minus 2 with modules. Yeah?
Yes.
Lambda n minus 1 is lesser than lambda n minus 2.
So let's see here. So lambda is bigger than this one. And this one is 0.
Yeah, then we should have lambda 1 minus lambda 2.
Then we should have lambda 1 minus lambda 2. So smaller.
N minus
Smaller should be. Yes, you're right. Lambda 3, lambda 2 here. Yes, like this. So this I just applied. Lemma 1. Now I would like to construct some bijection between Gelfand-Seytlin patterns and semi-standard Young tableaus, and this bijection actually should somehow make out of this somehow make x to x weight of t. Right? So we'll do this like simultaneously. So we need a bijection from Gelfand-Seytlin patterns to Young semi-standard Young tableaus of shape lambda. Let's try to construct it. So the procedure is like this. Well, we already have a shape. It's fixed. It's lambda. But now we need to. So take Gelfand-Seytlin pattern. Well, we need to. I need to give you a semi-standard Young tableau. I need to fill this shape Young diagram with numbers somehow. So here is my algorithm how I do this. So now, the recipe is like this. To the boxes of lambda I minus, so these are Young diagrams, so I can just delete some boxes. So everything which is in here but did not fit into the smaller one. You put.
I suppose it should be lambda I minus 1 without lambda i's, because we have the smaller one has more boxes.
The smaller one.
What is box?
Yeah, I plus 1 here, right?
Yeah, tableau has boxes.
I plus 1.
Like you could write Young tableau and this just. Box.
Yeah, so each.
I thought this lambda I is some row.
Yes. So this row, you can write a Young diagram corresponding to this row, right? Because it's so. For example, a Young diagram corresponding to the second row here has in the first row lambda 1 1 boxes, in the second row lambda 1 2 boxes, and so on. And do this, you have n Young diagrams. I also denote them as by the same letters. Yeah, everything here is non-negative integers, of course. And of course, I take one diagram, delete everything which is in the smaller diagram on the next step, and put the number put number n minus I inside. So this is my recipe.
It cannot be semi-standard.
Yes, so that's what we should worry. So I claim that this will be semi-standard Yan tableau. So we should now see why.
Is it true? Like,
yes,
can
it
we
is.
take something like, I don't know, 4, 2, like Yan tableau first, and then no.
So first of all, suppose this is your lambda,
Yeah.
and then you take. Let me try to take different color.
So I say that in one column we can have not strictly increasing.
Yes, but it is increasing. Is that clear?
I don't understand why.
So first, the easy part that it is increasing just because when you move from one Young diagram to another, which is inside, you go into this direction along rows and into this direction along columns. So if you put n inside here, then n minus 1 goes to this direction, and so on. So it is increasing along rows and columns. Now the question is why it's strictly increasing along columns.
I probably understand because I thought like I say like something like 4, 3, and then inner Yan tableau is just 1, but you can't take it like that. You need to take.
Yes. So this Gelfand-Zeitlin condition actually assures that your tableau is semi-standard, and I have an explanation.
I don't understand.
Yes, sure. What n would you like to take? 3, 4? 3. What is the... So 3, let me take 4, 2, 1. This is lambda. Then I take lambda 1. I take something in between 3, 2, and then 2. Okay. This is Gelfand-Zeitlin pattern. Let me now construct. So this is 4 to 1, right? So my partition is like my Young diagram is like that. 1, 2, 3, 4, 2, 1. Then I have 3, 2, right? 3, 2. So this is the color. So this is Young diagram for lambda 1. So this is lambda 1, 3, 2, right? So everything that fits inside lambda but not to lambda 1, I put n into these boxes, which is 3. So I put 3 inside here and inside here. Okay. Then I should consider the next one, which is 2. Right? Maybe another color. So this one. So this is lambda 0. Lambda 2, sorry. The green one is lambda 2. So, and then I take 2 and put inside here. And then 1 goes to here. So
when we wrote 3,
yes.
I equal to
I equal to 0.
So lambda 0 is everything.
Yeah, lambda 0 is this row. Yes, 4 to 1. Yes, is everything.
Yes.
And lambda 1 is 3, 2. So blue, I leave only everything that outside of blue. So this. Yes, yes. So because of this condition, so each local locally you have what, lambda ji greater or equal than lambda j plus 1 I, and you have lambda j here, but I plus first, right? And so you have this and this. So therefore, on the picture, you only can have the following situation. So this is your row corresponding to lambda j. So lambda ji, and then you have lambda. So maybe shorter. And then this. So you see, this will be lambda ji. This will be lambda j plus 1 I. And this will be lambda j I plus 1. You see? So that's how in pictures this locally looks like. So therefore, there's no box on the top of a box in this set minus. And that's why we have this condition, strict condition on columns. So no box on top of box in lambda I minus lambda I plus 1. So therefore, T is semi-standard. Now, look, our procedure actually gives us everything, because what is lambda minus lambda 1 there? It's exactly a number of n's that you put in here. So it will be xn to the number of n's in your Young tableau. What is and so on, right? So actually, after you do this, this bijection, you see immediately that the sum on the right-hand side is this sum. And that's it. Okay. All right. So next, so we finished this construction from the Fulton's book, Young tableau, which gives me a representation of V lambda as quotient. But we know that because of complete reducibility representation, if I have a quotient, then I have actually can realize it as a submodel. So how can I actually do this? And for that, I need to answer to that is given by what's called Schur-Weil duality. Let me see. Where do I have it? Not here.
True that the factor of J doesn't ruin the complete reducibility representation.
What do you mean doesn't ruin?
So we proved it for symmetric ln is not simple.
Yes, it doesn't. Yes. You just can, okay, let's talk about finite dimensional representations. And for finite dimensional representations, you can just see that it is always a representation of SLN tensor, this one-dimensional that we used today on the seminar. Maybe not where EII equals to 3, but where EII equals to some number. It's just, you just take this number arbitrary. Yes. Okay, so sure while duality. Okay, we need the following lemma. Let A be an associative algebra and V completely reducible representation of A. Denote also B to be the centralizer of A. How should I write it down? And A of V. The centralizer of A in endomorphisms of V. Everything that commutes with the action of A. Then there is isomorphism of A tensor B modules. V is isomorphic to some UI tensor WI. So here I runs over some set, say J, where these UIs and WIs are some irreducible representations of A and B respectively. Are some irreducible representations of A and B respectively.
Okay, I have a few stupid questions. So V is right or left A module?
B.
V. Or both?
Okay, let me just say both. Actually, so for us, no, let it be A left.
So for us, I think we need to that the A acts. So it is left A module and right B module, something like that. If we want it to be a tensor B module.
Yeah, kind of.
Here, what I mean by A tensor B is just okay. It's so A acts on the left factor, and b right x on the right factor. So why it's just simple as that. What's wrong with such description? So the question is, what is this thing, right? As a representation, as A tensor B representation, right? So far so this is over C. So this is some as a vector space. Now I need to explain on the right-hand side. So V is of course a representation of A and B, right? So therefore, this just means that it's both representation of A and of B, right? So it's A tensor B module. So this is also over C. So no.
There is some problems with tensor product of algebra of modules, but when we take tensor product of algebra, there is no problem.
Yeah. So I just need to say how AX on here and how BX on here. So AX only on the first factor and BX only on the second factor. So I think that actually defines everything.
Yeah, and they act like A tensor B acts on U tensor V as A U tensor B.
So A tensor and A tensor B, they are both unital, I should say, right? Okay, I assume that A is unital. Then you can look at this as A tensor 1 times 1 tensor B. And this you know how X on the second factor.
No, I
So.
it's by Leibniz rule acts or no?
No. So the main thing is that if I consider, forget about tensor product. I mean, what I'm saying is that this is both isomorphism as A modules and as B modules. So if I look at the right-hand side as an A module, it's just a decomposition of this module into irreducibles UI. And this is just multiplicity space. So you look at this as UI, UI, and then dimension WI as an A module. As B module, you look at this as direct sum decomposition WI dimension UI. So that's what it means. Yes, okay, so let's prove that. So first, I would like to consider V as an A module, and I know that it's completely reducible. Therefore, V is isomorphic, so I decompose it into irreducibles as a direct sum of UI, and I runs over some set. Well, it can be all representations, but okay, let me just take all that appear as a irreducibles inside V. Tensor, I can take the multiplicity space to be home from UI to V over A. Why is it like that? So let me do it in standard way. So it will be some copies of UI. UI1 plus UI2 plus and so on. And then the rest of the things. I claim that if I take UI, I can map it to V by just mapping it to the copy, to the JS copy. This will be homomorphism. This will be homomorphism of A of A modules.
Yeah, but why you can't map it to UJ?
Because of sure. So sure lemma. So let me denote this as Fj. Да. So by sure lemma, home A UI V is actually has basis F1, F whatever, so basis Fj. Moreover, I know. So this is I guess I would like to call some as phi. I don't know. And another statement. So of course, under this phi, Vx on here just on the first factor, right? But we also can understand how B acts. So B, I recall this is all endomorphisms of V which commute with A. But they're endomorphisms of V. So I claim that B acts on second factor just by composition. So this is a map from UI to V, and then you compose it, it will be mapped from V to V. So it acts here, right? So B acts on second factor by just composition. I don't know. Is it enough for you, or should I write more convincing formulas? Or more confusing formulas? I don't know. So this statement. Okay, so Mark.
To understand what? To understand the lemma.
No, is this statement clear?
That it acts on second.
So yes, first of all, it is clear that what it says, but why is it true? Is it clear? So under such an isomorphism, which I described here.
Don't actually understand. Like, what's the problem? It acts on second factor by composition. This doesn't say anything. It just acts.
No. The statement is the following: that if I consider action on the right-hand side just by acting on the second factor by composition, and action on the left-hand side because B acts on V, because it's in the morphisms of V, then the phi will be isomorphism of B actions. Okay. So let me write maybe some formulas. I guess this just follows from this, how this maps, like from the description of maps. At least I can convince myself by just this argument. So I guess you take right. So you map phi. What it is? You take U maps Uij. So you just fix some element Ui, which is inside UI. And uij is this element in jth copy. So it actually maps this to uj tensor f ui tensor fj, right? Okay, what did I write in here? Then L, say take L from B, right? B is again in the morphisms, inside the morphisms of V. I take on L, I act by L on uij. So this is the same as uij is just fj of ui, right? And I act on it. Just by definition, right? I take ui, and by fj, I map it. So this is composition of fj with L. So therefore, it's ui tensor fjl. Okay. Very well. So what we need to check? We need to check that home over A ui to V is reducible, is either reducible representation of B or 0. Well, since we took only set such that ui appears in there, it's not 0. So let's say that it is irreducible B module. I will do this by saying that B actually acts transitively in here, by showing that B actually acts transitively. Okay. So let me take two elements, F1 and F2, from home A ui V. So UI is irreducible, therefore these two are defined by where they send some fixed element of UI. So let me take UI inside UI without even. So I is fixed. So take U, and F of U, F1 of U is say V1, and F2 of U is V2. Okay, so then I take V1 and generate everything out of this vector by acting by A on it. So this is a vector in V, okay? And since V is completely reducible, it has some other representation that complements it. Say V tilde. So this is V. So this is one representation, this is another, of A. Okay, so then I define, we should go above.
Полеме Шуры.
Да.
Мне кажется, мы там пользовались тем, что то есть Лема Шура утверждает, что у UI нет изоморфизма нетривиального.
Ну да. Ну да. Нет, в смысле, из UI в UI я могу только, я могу только умножением на число действовать. Ну да. home из UI в UI это C, с home из UI в UJ это 0. Это и есть лемма Шура. Ой, значит так, хорошо. Значит, sorry. So define an element in B as follows. L acting on A, I'm using this decomposition. So L acting on AV1 is AV2. And L acting on V tilde is V tilde. It just doesn't move it for any V tilde from V tilde.
And what does it act on V2? Just.
So this is direct sum.
Yeah.
This gives me some map, well-defined map. So it doesn't move the second component, and the first one it just like that. V1 maps to V2, and I would like it to be homomorphism of A modules. Anyways, so just from here, it lives and it commutes with A. And then and also LF1 of U, right? This is L of V1. It is V2, which is F2 of U. But these two guys, F2 and LF1, they defined, so they are homomorphisms. So they defined by just one element that we with Vix. So therefore, LF1 is F2. So therefore, I found an element in B that which acts on F1 and gives me F2 for two arbitrary chosen elements, F1 and F2. So therefore, action is transitive, and therefore this thing is irreducible.
Это работает для конечномерных модулей. Или для модулей, у которых размерность не превышает.
Okay. It's finite dimensional modules. Yes. It should work over C and finite dimensional modules. All that. Yes. I think there are three parts. Some of them work for other fields. So I don't remember. But in our case, it's like finite dimensional modules. I never said it, but okay.
Забавно, что можно в конечной мере заменить на то, что размерность не превышает мощности поля. То есть конечная мерность не больше
полем там.
Нет, на конечном вообще не подходит, не алгебраический замок.
Что-то на C, да?
В общем, это все работает, если модули вот эти не превышают мощности континуума.
Круто, да, это круто. Это. Да.
Если закинуть FP разве континуум, там разве не счетное количество? Ну, FP звука.
Ну там, да, ограничение счетное.
Okay.
Может, конечно. Нет, там строго меньше.
So I claim that we already together proved Schur-Weil duality in a sense. So now I just need to. So first of all, we proved lemma, right? Now we just need to apply it to UGLN and SK. So SK. We proved. So recall that we had G, right? It's image of UGLN in the morphisms of V bar. And we had this think on a seminar that G actually equals to CSK. So this sorry. What I want to say endomorphisms over CSK of V bar.
Yeah.
Yes. So we prove that it is a centralizer of the action of SK on V bar. Right? So if I take now A to be SK, CSK, and if I take representation of V to be V bar, so this is a group algebra of finite group, and every finite dimensional representation is completely reducible. It's like a Mashke's theorem. So I can apply Liam. So okay, let me write it down. Yes. Да. Там можно строить проекторы прям явно. Усреднением по группе. Yes. So V bar is completely reducible CSK module, and therefore we can apply lemma. We take A to be CSK, we take B to be G, right? And V is V bar. And we can make the following conclusion. Sorry, let me find what I would like to write. Yes. So V bar is isomorphic to direct sum of S lambda tensor V lambda. So here lambda is partition of K. So this thing is what's called Specht module. So all irreducible finite dimensional representations of SK, they are Specht module, then they are labeled by partitions as well. Partitions of K. Okay, so here V lambda is either irreducible representation of GLN or zero. So question is who is V lambda, and for which V lambda is not zero, right? So it's some reducible, but we know all reducible representations actually, right? Of course, we would like to see that it is a representation of highest weight lambda with some condition on lambda. So question is who is V lambda? for that, we just need to remember what is Specht module. So it's actually S lambda. It is C of Sk acting on Young symmetrizer. So not acting, but it's left cassette corresponding to with a representative Young, which is Young symmetrizer. So the question is, who is sim lambda? I don't know if students study that representations of Sk. Not a finite group, but representations of symmetric group. Ah, okay. So this is some statement. So yes, exactly. So let me define what it is. So this thing is called, it is also an element in here, right? So you just take this element and multiply by everything from CSK. So this is some vector space, and it's clear how Sk acts on it, right? Just no. So this thing is called Young symmetrizer. Okay. So what is this? So I need to, so it is actually product of two things, A lambda and B lambda. Here B lambda is a sum over some subgroup of Sk, which is I denote by Q lambda, sine sigma. So Q lambda here, this is, well, I take Young tableau T, which we already saw before. So we have 1, 2, 3, 4, and so on, 5, 6, so like that. So I put numbers in increasing order from left to right, from top to bottom. Then Q lambda is all permutations of columns in T. So this is a subgroup in Sk. So there are the last box is K here. So Sk how it's defined? It permutes this alphabet from 1 to K. So I define a subgroup that only permutes elements within only within columns of T. So I cannot permute 1 and 2, but in Q I have element that permutes 1 and 5, for example. So first I anti-symmetrize with respect to columns. So that's what I do. And then I symmetrize with respect to rows. So A lambda is actually sum over sigma in some other subgroup, P lambda, sigma, without sign now. And P lambda, it is all permutations of rows in T. Okay, so this is the definition. And so that's how you construct irreducible presentations of symmetric group.
Is it a submodule of C of a set?
it is
Here we have the lambda.
it is a submodule. So SK contains all irreducible submodules inside. Its own. So see SK, it is a module of itself, right? It's a regular module, right? So it's actually a representation theory of finite groups. So CSK, I should say CSK is a module, right? It has decomposition. I think like this. If I remember everything correctly. So actually, CSK as an algebra, it's isomorphic to endomorphisms of S lambda direct sum over lambda partition of K. So that's why they say that every finite dimensional. Okay, let me not say anything stupid. Okay. Yeah.
A lambda should be sine sigma.
Where?
A lambda.
No.
There's
No sign. So everywhere in our story you have anti. So you anti-symmetrize along columns and symmetrize with respect to rows. You can see it actually from our previous constructions as well. Okay, so we have this. Then another statement that I will not check is that actually this is idempotent. So it's a projector, sorry. Okay. So what I would like to see is that, yes, so now let me go back and see what is V lambda. So recall that V lambda was, where should I go? Should go here, yes. V lambda was home over Sk from S lambda to V bar. So consider some element F from here. So let me just take this F and define a map from F to such an element. I put into correspondence vector in V bar, which is F of C lambda. So F is in here. It's a map from S lambda to V bar. In S lambda, it is this thing. I just take one in here, C lambda is in there. So, and I send C lambda to whatever it sends it, and call it VF. It's a vector in V bar.
So like we construct a map from V lambda to
Yes.
V bar, or what?
So I construct a map from V lambda to V bar. Exactly. Maybe I even would like to call it somehow. Each time I call a map phi, since we did not have phi for a long time. Let me call it phi again. Yes, and so this is injective, and it is homomorphism of GLN modules. Injective homomorphism of GLN modules.
So it's like evaluation in C lambda.
Yes, yes. So if it's injective, it's clear, right? If they coincide in here, then I mean, this is an irreducible presentation again. Yeah, and then they coincide everywhere. And then on V lambda, I act by composing, which actually means that I take this, the result, and act by my matrix from GLN.
Yeah.
So it's just like that. So I would like to claim is that image of phi is exactly C lambda V bar. So it's an image of an action of Young symmetrizer on V bar. Well, I guess I would like to see two ways. So proof of claim.
How C lambda acts on V bar?
It is an element of CSK. SK acts on V bar.
Oh, it's an element of CSK. Yeah.
Yes.
That's true. Okay.
So we do something. We like symmetrize and anti-symmetrize. So it's actually something happens. So proof of claim. So I guess I would like to prove two-way inclusion. So inclusion in this, I would like to see that if I take something like VF, that it is inside C lambda V bar. I take f of C lambda. It is the same as f of C lambda square. And it commutes with the action. So it's C lambda f C lambda. This inclusion is here. What about this one? So I take an element. I take an element V in V bar to make it. So this thing is still in V bar, right? It's just C lambda x from V bar to V bar itself. And what's in the image? In the image, elements V such that C lambda V is V itself. I project, it's already there. Then let me define. So I go back and define F. I define F as follows. F A C lambda is AV. So if this is well defined, then it is a homomorphism of, it is in here,
Yes.
right? So we would like to prove that it is well defined, which is also almost obvious. Right, if I take some A and B such that AC lambda equals AC lambda equals to BC lambda. I need to check that is it true that AC lambda AV equals to BV. But of course it's true because this is the same as AC lambda V equals to BV. C lambda V, because V is in C lambda V is the same thing.
So we take such V in V bar that it's
Yes. And like this is the same as taking something from the image, because it's a projector. But then, of course, since AC lambda equals BC lambda, so what? So this is the same as this, but this is true, because we started with this assumption. Okay. So what do we got? We have now that V lambda is C lambda V bar, right? It's already something. So I explicitly described what is V lambda as a representation of GLN. Because this is injective homomorphism of representations, and the image is C lambda V bar.
V lambda. Yeah,
Yes.
it's not V bar. Okay.
Yes. But then what's left is just to take and find single vector here and prove that it is not zero and that it is singular. But this is just some, it's just the same thing that we did already, but easier. We don't use Sylvester lemma anymore. It's easier to prove it directly. So the singular vector here, we already know that it's reducible, right? So just need to find the highest weight. Again, I take VT0, where T0 is our favorite semi-standard Young tableau. 1, 1, 1, 1, 2, 2, 2, 2, 3, 3, and so on. So I claim that so claim 1. So I don't know how much time is left. So it's an exercise. We can check it here, or I can give it to you next seminar. I don't know. What do you like better? Better to finish or what?
I think better
To check it now or what? Not now. Okay. So I claim that this is not. So first, claim 1. It is killed by EIJ. So if I take C lambda of this and take EIJ with I less than J, then this is 0. And claim 2 is that C lambda VT0 is not 0. And it definitely has weight lambda.
It's like you need to understand what C lambda actually is.
Well, you know what it is. You just go to this formula, and you can, you can rewrite it somehow to see this and this, actually.
Yeah, but like all permutation of rows on T0 is nothing. Yeah. There is no permutation.
Yes, that's exactly why. So each time you just some multiple of it. Мы все доказали. Ну, в смысле, если вот эти два клейма проверить, мы доказали, что V лямбда это ну, что образ действия симметризатора Юнга на V с чертой это L лямбда. Ну и как с симметрическими там и значит, внешними степенями пространств. Их можно реализовывать как quotient, а можно реализовывать как подпространство. Вот мы и так сделали, только теперь в более общем случае.
Сейчас, да, окей. А для чего мы это делаем?
Ну, это некая, вот, это некая другая... Кстати, вот в большинстве литературы скорее вот таким пользуются. Просто здесь вот сложнее увидеть базис вот этот из полупростых таблиц Юнга.
Тут что SSYT базис.
Да.
Когда мы это доказали?
Мы это доказали, когда доказали формулу, что S лямбда там от x это сумма x. Вот здесь положите, значит, x равняется единичке. И получится здесь это просто будет количество полустандартных таблиц Юнга, а это будет размерность L лямбда, если x положить единичкам. То есть мы вообще все доказали, если вот это проверить.
Двойственность Шура-Вейля — это то утверждение?
Да,
Двойственность Шура-Вейля, да, это утверждение о том, что... Да, это вот такое разложение. Ну, значит, в большинстве случаев люди говорят для каких-то неприводимых представлений лямбда. Потому что, ну, обычно это написано не в книжках про представления ЖЛН, а в книжках по представлениям этой симметрической группы. Вот. Ну а мы даже сказали, кто такие лямбда. Ну и на самом деле понятно, какие не нулевые. Теперь это все разбиения К такие, что там не больше, чем n строчек здесь играют. Вот. Ну, потому что если... Ну, наверное, понятно. Вот. Еще, значит, это обычно вот эта часть двойственной Шура-Вейля, и еще там говорится, что централизатор УЖЛН, это что CSK и УЖЛН, они взаимные централизаторы друг друга. Вот. Это, ну, мы доказали, что УЖЛН — это централизатор CSK, и наоборот тоже правда, что CSK — это централизатор УЖЛН. И это на самом деле достаточно быстро следует из вот такого разложения и из вот этого. Ну, я мог, как бы, это можно сделать, если было время. Вот. Ну, и это в более общем, вот эта лемма, которую мы доказывали, с вот этим утверждением, что, ну, с вот этим обратным утверждением, что они взаимные централизаторы. Таким более общем сеттинге, их там полупростых там, ассоциативных алгебр, это называется там, теорема о двойном централизаторе. Что централизатор централизатора — это обратно, как бы, это же алгебра. Вот. Там как бы одна часть — это вот такое разложение, а вторая часть, вот, что централизатор, он совпадает с... Вот. Угу. До свидания. До свидания.